Welcome to part 6 of Sound Basics. Last we left off, we talked about these composite or complex waveforms, and we learned about string modes and such. And we left off saying that you can combine these modes because they are all happening simultaneously. And then the result is you get this composite waveform. So we're going to look a little bit more at this because what happens is you have a pitch that's generally assigned by the first harmonic or the fundamental. That's where you get your basic pitch of the tone you hear. But then all these waveforms above will give you your timbre. So we're going to talk about timbre today. Now, for example, you see these composite waveforms. And again, remember, this is change over time. So changes in pressure over time. So you have this violin, and look how different they look. This is the trumpet, this is the flute, and this is the oboe. Now, one thing to keep in mind is these are still periodic waveforms. They just don't look like the sinusoidal waveforms that we're used to seeing. And all this complexity is basically what we were looking at before. It's basically a combination, the adding of all these sort of different modes, right? Whether it be a column of air or a string, right? So trumpet, flute, oboe, violin. And they all have their distinct timbre. So that particular combination, and here's a different representation of that. These are the different harmonics present and the relative amplitude present in the basic sound. You know, not like every note, but basic sounds. You know, oboe has this kind of outlay of harmonics. So the fourth harmonic, there's a little bit of a peak there. It's louder. Clarinet has this kind of thing, generally speaking, right? The clarinet, because it's a closed tube system, has odd harmonics, and generally speaking, the flute has even all the harmonics there, you know, and this kind of very gradually descending amplitude structure. Trumpet has a couple peaks like this. So you can kind of think about instruments or sounds in general or timbres as being kind of a recipe of these modes. In the case of pitched sounds that have a harmonic series above them, so columns of air or strings and such, because of the natural modes of resonance. And other forms, like the human voice has a different kind of outlay of harmonics. All right, so this is how we think about timbre. This that sound color. This particular combination of various harmonics gives oboe its particular sound. So let's have a look at this video, and it's pretty good. It shows this spectral representation of different sounds. Okay, and so I guess the different colors represent the intensity of different energies, and then you're seeing the frequencies up here, right? So you have your fundamental frequency, and I think it's the same for every note here, every instrument, and then you have all your various. Remember, it's like a recipe or a cocktail. All your various harmonics and the relative intensities all the way up. Okay, so let's have a look at that. So you noticed also This video is great, by the way. They give you a really nice representation of these sounds. You notice also not only do you have this kind of spectrum, right? You have a load of harmonics, or sometimes there might not be harmonics above, but you have a load of partials above the fundamental. But also you can see the fluctuation that happens over time. So that's how the sound color is changing. Even though the note is the same, you get this kind of fluctuation over time of the different partials. All right? And then you have things like the shakuhachi, which has these kind of broader, right? These broader peaks. Or you have something like, I think, it's coming up the accordion. They tend to be a little bit narrower there, right? And those lend it their particular sound quality or timbre, sound color, right? Yeah. So we notice the sitar, for example, and then just these changes that happen over time, and they are represented. So we tend to talk about this outlay of the different partials as a spectrum, a sound spectrum, meaning that there's energies at several different frequency points, several different frequencies. There's a bunch of energy, and that sort of combined spectrum, all that combined, gives the particular sound that you're listening to. So it gets a lot more complex when you bring in timbre or the spectrum, because you do get these changes that happen over time. But I'm sure you're familiar with maybe not this particular thing, but some examples like in the EQ and stuff like that, where oftentimes they show energy at different frequency ranges, right? And the important, or not the important, but the stuff we learned in the last video, we're talking about pitched and harmonic instruments. So all these have some sort of harmonicity, and you're basically just hearing the one pitch, right? So again, these are more or less harmonics to the first harmonic or fundamental, and they reinforce, like we learned last video, they reinforce that one pitch. So they all have the same pitch, yet they all have a very different sound. All right, and so that's what we mean when we start talking about timbre. That timbre is really crafted or created through this sound spectrum, this combination of energies at different frequencies, and they tend to be harmonically related to the pitch or the fundamental frequency. All right, not only do instruments have these complex waveforms, or these, but also you can make electronically ones that really aren't found necessarily in nature. You can generate electronically these. So here's a nice little thing from the University of Oregon, and they show you how to construct, like, for example, a sawtooth wave. So a sawtooth wave has this recipe, or has this sort of equation, so that each one has 1 to the n, 1 over n amplitude. So the second harmonic has half the amplitude of the first, or half the strength. The third has 1/3, the fourth 1/4. So if you generate the sine tones, so basically each of these are sine tones. If you generate a spectrum of sine tones, with one being, say, if this is 100 hertz, the 2 will be the second harmonic, or 200 hertz, but at half the strength. 300 hertz at 1/3 the strength, etc., etc. You're going to get a sound that sounds like this, and you're going to get a resulting waveform like this, meaning that this represents the change over time in pressure in the air. So you're not really getting this sort of thing, but you're getting it all combined, remember, in a combined waveform altogether. So let's look at that. All right, and so that's the sawtooth wave, and it's that kind of buzzy sound we're quite familiar with. The next one is a triangle wave. All right, so it's called a triangle wave, just like the sawtooth wave is called the sawtooth wave because of its shape. All right, so let's see how that gets constructed. Now these ones have only every odd harmonic, so they don't have any even harmonics, right? And the odd harmonics are 1 over n squared, right? So this has 1/9 the energy. This has 1/25, 1/49 the energy, etc., etc. So let's listen to that. And that's how a triangle wave sounds. Let's do one more. I think there's a square wave, a rectangle wave. Okay, now they again have just odd harmonics. And I'm trying to see what the relationship is in terms of amplitude. Okay, well, let's listen to it. Okay, and I think that's it. Right, very good. So also, you can have non-harmonic or inharmonic partials. So we won't call those harmonics, but you can have a spectrum above, or a certain kind of spectrum, a layout of energy at different frequencies that don't have these whole number ratios of a fundamental frequency. Okay, and those tend to give sounds that aren't necessarily pitched. They're very vague in pitch, or sound more like they have several pitches going on at the same time. A classic example of this is the bell. When you hear a bell ring, you can't really sing the pitch itself. Sometimes it sounds like 2 or 3 pitches, yet it has this sort of like timbre. It has a sound color. Jean-Claude Rizet, a composer and technologist, inventor, came up with, he developed these recipes for bells. Okay, and you'll notice here in my supercluster patch, you have, these are the ratios of harmonics. So instead of whole number ratios like 1, 2, 3, 4, 5, 6, 7, you have a harmonic at 0.56, and then you have 1.19 times, 1.7 times the fundamental frequency, 2.74, 3.76, 4.07. Okay, and this creates a certain kind of sound, which sounds a lot like a bell. And he kind of pioneered this technique known as additive synthesis and analysis resynthesis. So you take something like a bell, analyze, and get its spectrum, get the kind of change over time of different energy at different frequencies, and then resynthesizes by generating these pure tones at all the different frequencies. Okay, and we'll learn more about that, but let's listen to the Rizet bell. And Rizet would go on to use these models to create some really interesting compositions and create some really interesting sounds using this technique called additive synthesis. So if we look at the sound spectrum of a flute, and we've already seen examples of something like this, you see here has these different partials and a particular outlay, right? And we've called this thing the sound spectrum. That has these change over time, but it's essentially like a fairly complex, very kind of intricate recipe or cocktail. And what Rizet did, for example, was to be able to like recreate these by generating energy in a very similar pattern. So for the bell, he analyzed the bell and then used oscillators and such, used digital audio to generate energy at these different areas and have them change over time as well. So to kind of recreate those sounds. But then when you already have those models within your, like Super Collider or different electronic music kind of devices, then you can manipulate those models and get kind of interesting, weird sounds that maybe don't occur in nature or don't sound like stuff you normally hear. All right. So, but let's talk a little bit about, just so everything's clear, we've mentioned this before, but a sine tone, right, is a representation of a sine tone of change over time. And you have this kind of the sinusoidal change of air pressure. So it becomes compressed and refracts, compression, rarefaction over this very smooth sort of sinusoidal curve. Now, when you do that, when you generate oscillation like this, in this fashion, you get a very pure tone. And if you were to take a spectrum analysis of a sine tone, you wouldn't get any energy at any other place except, so for example, this is a 440 sine tone. I only have energy at 440 and no upper partials, right? No spectral energy, so very pure tone. So that brings me to Joseph Fourier, Jean-Baptiste Joseph Fourier. He developed this a Fourier theorem, what we call the Fourier theorem. And basically, he postulated that you can take a complex sound and you can break it down. Basically, what we've been saying, break it down into individual sinusoidal parts. So you can create a bunch of sine waves that don't have any spectral energy, don't have any harmonic energy, and you can create you can use individual sinusoidal waves at different frequencies, at different amplitudes, and again also different phases, and you can combine those and create a complex sound, right? And you can go back and forth. So you can take this complex waveform that we've been looking at, these changes over time, right, that are still pitched because they're periodic, they repeat, but they have these kind of weird fluctuations. You can use that and then break that out into individual sinusoids. Okay, and that is the Fourier's theorem. And actually, it's like a mathematical thing to do with signal processing, not necessarily to do with sound, but it's very helpful in music, and especially electronic music, to manipulate sound. So let's just read here. The theorem says that any repetitive wave can be reproduced exactly by a Fourier series of single frequency waves, so those are the sine tones, with different amplitudes. Fourier's theorem also includes a mathematical formula for finding the amplitude of each different frequency wave in a series. That is how a frequency spectrum is determined. Fourier's theorem states that a periodic function, so a periodic function being something that essentially is pitched, which is reasonably continuous, may be expressed as a sum of a series of sine or cosine terms called the Fourier series, each of which has a specific amplitude and phase coefficients known as Fourier coefficients. Okay, so there's the two domains. We would call this the time domain. So this is change in amplitude or change in air pressure over time. Now this is a representation over here on this side of the frequency domain. So if you take a snapshot of time, you notice there's energies at certain frequencies. Okay. Now Fourier's theorem, or what he developed called the Fourier transform, which we'll look at in some detail in the next video, is able to change back and forth between. He's able to take complex signal changing over time, as long as it's periodic, and transform it into a collection of these sinusoids with differing amplitudes and phases. All right, and it's just two ways of looking at the exact same thing, and he gives us a mathematical equation for that. Okay, so here is an interesting example of the Fourier transform or Fourier theorem, Fourier series in effect. So essentially, you can take something at like different pitches and recreate a different kind of sound. So these folks here in Austria, in Graz, Peter Ablinger and his crew, they developed this mechanical piano. Basically, it's a robot on top of a piano that plays very, very finely with great deal of accuracy the different piano keys at different volumes too. So essentially, it's like a resynthesis, but instead of sine tones, like a resynthesis machine. But instead of sine tones, they're using the individual piano keys. Now, a couple of issues, I don't want to get too into the weeds here, but a couple of issues is under the Fourier theorem, you're essentially can have an infinite number of sine tones, right? And you can have a bunch of frequencies that might fall in between the gaps between two piano keys. But you'd be surprised at what you can get away with a fairly blunt number of available frequencies you can get away with. So They've created this robot. They fed it these kind of Fourier analyses, and they're able to make a piano not sound like a piano anymore necessarily. So let's have a look at that.
Alles klar? Wohl kaum, das lässt sich aber ganz einfach ändern. Schon erstaunlich, wie genau plötzlich die Worte der Deklaration für einen internationalen Gerichtshof gegen Umweltverbrechen verständlich werden. Wien Modern war eine von 10 kulturellen Institutionen, die um einen künstlerischen Beitrag für die Veranstaltung im Dogenpalast in Venedig gebeten wurde.
Right, so by using the piano and this robot that they built for it, they're able to use the Fourier transform or Fourier series, however you want to think of it, Fourier theorem, to resynthesize this voice. And it neither sounds like a voice, it doesn't sound electronic so much, and it doesn't necessarily sound like a piano anymore either. It's kind of this eerie kind of voice, a very interesting process. And that's using sort of the Fourier transform right there. All right, so that will do it for this section on timbre. Please join me for part 7, where I'm going to delve into the mathematics behind the Fourier transform, but try to keep it at a real layman's explanation. All right, thank you.